Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today we're going to be continuing our lecture on bonding and chemical interactions. We left off in the previous video at Lewis structure, so let's get started there. The simplest model for describing the bonding in a molecule is its Lewis structure, which shows how the valence electrons are arranged among its atoms. Now what we want to do is learn how to draw Lewis structures, so there's a couple of rules that we want to put in place that we can follow to make sure that we do it correctly every single time. The first rule is to sum up the valence electrons from all atoms and make sure you take into account any positive or negative charges. Then the second rule is to determine which atoms are connected. So here, there's a couple of things I want to point out. The first thing is that the central atom is usually listed first. In addition, something else to keep in mind is that the less electronegative atom is usually the central atom. In addition, in oxyacids, such as nitric acid or phosphoric acid, each hydrogen atom in these kinds of molecules is going to be attached to an oxygen atom, and then that oxygen atom is going to be attached to the other central atom. Now, in some cases, the formula might describe the order in which the atoms are bonded, and in that case, that would make it easier for us to determine which atoms are connected. But keeping a lot of this information in mind is going to be important, especially that the central atom is usually listed first, and the less electronegative atom is usually that central atom. The third rule is to distribute the total number of electrons that you determined in step 1 by proceeding in this specific order. First, you connect the atoms, keeping in mind that each bond represents 2 electrons. Second, complete the octets on the outer atoms. And then last, put any leftover electrons on the central atom, grouping them in pairs. Now, this may give some atoms more than an octet. That's okay, as long as the atom with more than an octet is in the third period or below. Then last but not least, check to see if the central atom has at least an octet. If the central atom has less than an octet, use electrons from the outer atoms to form double or triple bonds until an octet is achieved. And then for a final check, having completed these steps, verify that your Lewis structure possesses the correct number of electrons. If a Lewis structure is drawn incorrectly, it almost always has an incorrect number of electrons. Now, again, I want to remind you about formal charges. It's important to note that the number of valence electrons attributed to an atom in a Lewis structure may differ from that in a neutral atom due to the bonding interactions. And this difference results in a formal charge, which helps in understanding the electron distribution within the molecule. The formal charge of an atom, it can be calculated again using this equation right here, where V is the number of valence electrons in a free atom. This part is the number of lone pair electrons. And this non-bonding, this is the number of bonding electrons. So what you have is that the formal charge is the number of valence electrons in a free atom minus the number of lone pair electrons minus 1/2 the number of bonding electrons. Now, with that, let's go ahead and explore these rules by doing a couple of examples. All right. What we're going to work through first is phosphorus trichloride. All right. Remember, step 1 here is determine the total number of electrons in the molecule or ion. Now, phosphorus has 5 valence electrons. You can figure that out by just going to the periodic table. All right. Identifying where phosphorus is. It is in group 5, and this is the numbering that we did when we omitted the transition metals. It's in group 5. Therefore, phosphorus has 5 valence electrons. What about chlorine? Chlorine is in group 7 right here. All right, that means it has 7 valence electrons. So then for this first part, where we're determining the number of electrons, we're going to have to add up 5 valence electrons for phosphorus, and then 7 electrons for chlorine, but we have 3 of them, so 7 times 3. That's going to equal 21, and then we can sum up 21 and 5 to get the total number of valence electrons. This is going to be 26 electrons. Then the next step is we got to figure out which atoms are connected. Here, phosphorus is the central atom. All right, it is less electronegative than the chlorine atoms, so it's going to be the central atom. Not only is it listed first, but it's also, again, less electronegative. So we draw phosphorus here near the center, and we're going to surround it with 3 chlorine atoms. Wonderful. Now, step 3 says to distribute the total number of electrons that you determined in step 1 by proceeding in this order. So step 3A is to first connect the atoms. So now we've connected phosphorus to the 3 chlorines. Remember, each bond has 2 electrons. So far in step 3A, we have used up 6 of our 26 electrons. Then step 3B is to complete the octets on the outer atoms. So what we're going to do is we're going to give the chlorine atoms an octet. All right, so that means since there is a bond right here between this chlorine and this phosphorus, that's 2 atoms. All right, that's 2 electrons. So then we're going to add 2, 4, 6 around the chlorine atom. All right, and this bond is 2 electrons. So now chlorine has a full octet. And we're going to do that with every single chlorine atom. We're going to give it a full octet. Now what we've used up is a total of 24 out of the 26 electrons that we had. Step 3C then is to put any leftover electrons on the central atom and be sure to group them in pairs. We only have 2 more electrons left, so we went ahead and we put them on the central atom. All right, so there we have it. Now we have used and placed 26 out of the 26 valence electrons that we had to begin with. The last step, step 4, right? This is where you kind of do a quick check. If the central atom has less than an octet, give it an octet by forming double and triple bonds from the electrons on the outer atoms. In this structure right here that we've drawn, the central phosphorus atom has 3 bonds and 1 lone pair. Therefore, it has an octet because 2, right? Because 2, 4, 6, 8. And so this Lewis structure is correct. We did it correct. We don't have to form any double or triple bonds to accommodate for the octet rule. It is already satisfied the way we drew it after step 3. Wonderful. So that's how we do it for this molecule. Let's do another one. All right. This one right here, H3PO4, phosphoric acid. Let us draw the Lewis structure for this molecule. Again, we start off with our good old step 1. Determine the total number of electrons in the molecule or ion. Hydrogen has 1 valence electron, but we have 3 hydrogens, so that's a total of 3 electrons. Phosphorus has 5 electrons, and there's only 1. And then oxygen actually has 6 valence electrons, and there's 4 of them. So 6 times 4 is 24. Now we can sum this up. 24 plus 5, that's 29, plus 3, that gives us a total of 32 valence electrons. Now we can move into step 2. Step 2 is determine which atoms are connected. Now this is an oxy acid, so each hydrogen is attached to oxygen, and then each oxygen is attached to the central atom. The central atom here is going to be phosphorus again because it is the least electronegative. It's going to be connected, all right, it's going to be connected and surrounded by the 4 oxygen atoms, and then the hydrogens are associated with the oxygen atoms. Now we can move to step 3A. All right, remember step 3 in general is the goal is to distribute the total number of electrons that we determined in step 1 by proceeding through this order of A, B, C. So step 3A tells us to connect the atoms. So now we're going to connect this phosphorus to this oxygen, and this phosphorus to this oxygen, and this oxygen, and this oxygen, and then the 3 hydrogens are connected to the oxygens. Remember, each bond is 2 electrons, and we've drawn a total now of 7 bonds. So we've used up a total of 14 electrons so far out of our 32. Now we can move into step 3b, complete the octets on the outer atoms. Now remember, when hydrogen has 2 electrons, that's considered an octet for hydrogen. And hydrogen has this bond to oxygen, so it has its octet satisfied. Where we're adding electrons to the outer atoms, what we mean by that is to the oxygen atoms. The oxygen atoms are also outer atoms. So then we're going to try to complete the octet by drawing, all right, electrons on the oxygens to satisfy the octet rule. So for this oxygen that already has 2 bonds, 4 valence electrons, we just need to draw on 4 more. That oxygen satisfied its octet rule. And same goes for this oxygen as well, 2 bonds, so we add 2 lone pairs. Now that oxygen has a full octet. And same goes for this one as well. As for this last one, it only has 1 bond, so we need to draw 6 electrons around it to satisfy its octet rule. Now, with that drawing right there, we have accounted for all 32 electrons. So this third step, 3c, when it tells us, hey, put any leftover electrons on the central atom, we don't need to change the structure above because all 32 electrons are accounted for, so there are no leftover electrons to put on the central atom. Now, the fourth step allows us to check to make sure that phosphorus indeed has a full octet. The central phosphorus atom has 4 bonds, each one representing a pair of electrons. Therefore, it does have an octet, and the Lewis structure is complete. So this is the proper Lewis structure. Wonderful. Now, what we want to do, all right, is do another example problem. All right, this is going to be important to practice a lot, so, bear with me. We're going to do one more example for Lewis structure. For this first example, we want to draw the Lewis structure for HCN, hydrogen cyanide. All right, so let's just go ahead and follow our rules one by one. The first step we want to do is determine the total number of electrons in the molecule or ion. Now we have HCN, hydrogen has 1 valence electron, carbon has 4 valence electrons, and nitrogen actually has 5 valence electrons. So if we add up all of these valence electrons, we'll get a total of 10 valence electrons. Wonderful. Then the second step is to determine which atoms are connected. Now, carbon here is going to be the least electronegative, considering that hydrogen in these kinds of molecules has to be somewhere that is in the outer positions and not the central atom, because it can only have 2 valence electrons to satisfy its octet rule, quote unquote octet rule. All right, so then considering that hydrogen must occupy an end position of the 2 remaining atoms, carbon versus nitrogen, carbon is the least electronegative, and therefore it's going to occupy the central position. And so the skeletal structure looks like this. We have carbon in the center, and we have hydrogen that's bonded to the carbon on one side, and then the nitrogen. And so here in the third step, all right, in the third step, what we're going to start to do is distribute the total number of electrons that we determined in step 1, all right, by proceeding in a specific order. So step A, 3A, is first connect the atoms, keeping in mind that each bond has 2 electrons. So now what we're drawing out is hydrogen bonded to carbon, bonded to nitrogen, and this accounts for 4 valence electrons already. Then in step B, all right, we want to complete the octets on the outer atoms. Now, hydrogen, remember, it just needs 2 valence electrons. So we're not going to add any more electrons to hydrogen because it already has those 2 with this bond to carbon. But nitrogen, this is an outer atom that doesn't have a full octet. So we're going to add some of those valence electrons to nitrogen to complete its octet. So that means we're going to add 1, 2, 3, 4, 5, 6, and this bond is 2 more, so for a total of 8. But now what has happened is we've drawn in all 10 of our valence electrons. Now for step 3C, any leftover electrons we would put on the central atom, but we don't have any leftover electrons, no leftover electrons. So for step 3, we are essentially done. Now we move into step 4. Now this is where it gets interesting. Step 4 says if the central atom has less than an octet, give it an octet by forming double and triple bonds from electrons on outer atoms. All right, so now what we need to do is, well, carbon only has 4 valence electrons when it needs 8. So how can we satisfy carbon's octet rule? Well, we can take this pair of lone pairs, all right, this pair right here of electrons, and let's form a double bond. All right, if we form a double bond, now our carbon has 2, 4, 6 valence electrons. We need a little bit more to satisfy carbon's octet rule. So let's take another pair of electrons and let's form a triple bond. So now we should have hydrogen bonded to carbon, and carbon is triple bonded to nitrogen, where nitrogen has just 1 pair of electrons. Now the carbon's octet has been satisfied, and so is nitrogen's. Us forming those triple bonds doesn't take away from nitrogen's full octet. So hydrogen has its 2 valence electrons, carbon has 2, 4, 6, 8, and nitrogen has 2, 4, 6, 8. So everything is good. Now we are done, and this is the Lewis structure for hydrogen cyanide. Wonderful. Let's do this next example problem. This one says calculate the formal charge on the central nitrogen atom of ammonium. Now, here's a fun thing. If you want to try your luck with Lewis structures, pause the video. NH4 plus, try to draw that out. All right. And I'm just going to go ahead and draw it out, the proper Lewis structure, so we can just focus on learning how to calculate the formal charge. So if you want, you can pause the video now, draw out ammonium, and then compare it to what I'm going to draw right now. So ammonium, nitrogen is going to be that central atom. It's going to be connected to the 4 hydrogens. All right, and this will account for all of the valence electrons that we have to play with. All right, and this molecule has a positive charge. We're trying to calculate specifically the formal charge on the central nitrogen atom. So what we're going to focus on is the nitrogen. How many valence electrons does nitrogen have? Nitrogen is in group 5 when we do the numbering where we omit the transition metals. Nitrogen is in group 5. It will have 5 valence electrons. Now, in this molecule, nitrogen has 4 bonds. All right, it has 4 bonds to hydrogens, which means that it has 8 bonding electrons. So the number of bonding electrons is 8. And it has no lone pairs, so the number of non-bonding electrons is going to be equal to 0. Now, all we have to do is plug it into our equation, the one that we said formal charge is equal to the number of valence electrons minus the number of non-bonding electrons minus 1/2 the number of bonding electrons. So here we just plug in these values. The number of valence electrons is 5. We don't have any non-bonding electrons, so that's 0. Then we subtract this from 1/2 and the number of bonding electrons, which is 8. So we have essentially 5 minus 0 minus 1/2 times 8. This is just going to be 5 minus 4, which gives us a positive 1. That means that the formal charge on the nitrogen atom in ammonium has a formal charge of +1. Now, you can also use logic to determine formal charge. So as drawn, nitrogen has 4 bonds. Assuming equal sharing of the electrons in the bonds, this means that nitrogen has 4 valence electrons, and in its normal state, we know that nitrogen has 5 valence electrons, and so therefore nitrogen has 1 fewer electron than its normal state, and thereby has a +1 charge. You could do it either way. You can work out the math, or you can kind of work through it logically, whatever works for you, right? To each their own. So those are our 2 example problems. And with that, we actually want to move into a new topic on resonance. Now, Lewis structures are very simple models, so we shouldn't be surprised to find out that they don't always describe a molecule's bonds effectively. Resonance occurs when more than one valid Lewis structure can be drawn for a particular molecule. So, in other words, resonance structures are multiple Lewis structures that represent the same arrangement of atoms. They only differ in the specific placements of electrons. These structures are indicated by a double-headed arrow between them. And the actual electronic distribution in the molecule is going to be a hybrid of all possible resonance structures. And so this means the real structure of the molecule is a blend of all of the resonance forms. So let's work through this example that we see right here for NO3 minus. All right, NO3 minus. The first thing that you would do is you would draw the Lewis structure. Nitrogen is going to be your central atom. It's going to be bonded to 3 oxygen atoms. And this molecule has a total of 24 valence electrons, 5 from nitrogen, 6 from each oxygen, and there is a total of 3 for 18. Plus, it has a -1 charge, so we have to accommodate for that. That's an extra electron. So 5 plus 1 plus 18, that gives us a total of 24 valence electrons. Now, each of the resonance structures show 1 double bond and 2 single bonds between nitrogen and oxygen. But the placement of the double bond changes among the structures because you can draw any version of this and it would be correct because it places and uses all 24 valence electrons. And if you place the double bond here or here or here, you are still satisfying the octet rule for all of the atoms. And so in the case of NO3 minus, you can draw 3 varieties of the Lewis structure. Now, this is what we call resonance structure. So we can draw all 3 varieties and we kind of put them together with this double-headed arrow to signal that. So in one resonance form, the double bond is between nitrogen and one of the oxygen atoms with single bonds to the other oxygens. And in the other forms, that double bond moves places. So in one structure, it's right here. In one structure, it's right here. And in another structure, it's right here. The real NO3 minus molecule, the actual structure for it is going to be a resonance hybrid, where the electrons are actually delocalized over the 3 oxygen atoms. Each NO bond here is identical and has a bond order that's actually between single and double bond, because the actual structure is going to look like a combination of all 3 of these. And so if you were to draw it in a way that would indicate that it looks like a resonance hybrid, you would actually put dotted double bonds everywhere, all right? Because the electrons are delocalized. So this is another way to convey that same information. Now, in this example, the cool thing is that each resonance form contributes equally to the hybrid towards what the molecule actually looks like. Each one contributes equally. However, all resonance forms do not always contribute equally to the hybrid. Yes, the real structure looks like a mix of resonance structures, just like a child will look like both their mother and father because they're going to have features from both their mother and father, but it will sometimes resemble one structure more than the other, just like a child might maybe look more like mom than dad. Now, in this case, it's important to identify the most significant resonance structure. And what we're going to have to do here is learn the rules for identification. How do we identify which structure is the most significant resonance structure? So here what you see is the rules for identification listed in order of most important to least in the manner of identification. And so if you are wondering, how did we know that all resonance structures for NO3 minus contributed equally? How do we figure out if that's true for other molecules or not? How do we work and figure out the resonance structure hierarchy? These rules will help you do just that. So the first rule is called satisfying the octet rule. Structures in which more atoms satisfy the octet rule are more stable and contribute more to the resonance hybrid. The second thing that you would want to check is formal charges. Minimizing formal charges is going to be important. Structures with small or no formal charges are preferred over those with large formal charges. And the formal charge can be calculated using the equation that we've used previously, right? Formal charge is equal to the number of valence electrons in a free atom minus the number of lone pair electrons minus 1/2 the number of bonding electrons. So that's the first two rules. The third is placing negative charges on electronegative atoms. Structures where the negative formal charge or charges are placed on more electronegative atoms, like oxygen, are more stable than those where the negative charges are on less electronegative atoms. So these are the things that you want to keep in mind when you're looking at all the resonance structures for a molecule and trying to determine which one is going to contribute the most. All right, check the octet rule, minimize formal charges, and make sure that if there are formal charges, that the negative charges are on the electronegative atoms. Now, if criteria 1 through 3 do not help you distinguish between structures, then they all contribute equally to the resonance hybrid. So keeping these in mind, it's going to really help you tackle problems. And that's exactly what we're going to jump into next, a practice problem. Write the resonance structure for NCO-. To begin to tackle this problem, we're going to follow the steps that we put into place for drawing Lewis structures. And we're going to start from there and work our way into drawing the resonance structures for this molecule. The first step is to go ahead and determine the number of valence electrons, the total number of valence electrons. From nitrogen has 5 valence electrons. For carbon has 4 valence electrons, and oxygen has 6 valence electrons. This molecule also has a minus charge, so that means it's gained 1 extra electron. So we have to accommodate for that as well. So what we have is 5 plus 4 plus 6 plus 1 for a total of 16 valence electrons. Now the second step is to go ahead and determine which atoms are connected. Here, carbon is the least electronegative of the 3 given atoms, so that means that the carbon atom occupies the central position here. We have carbon in the center, and it's going to be surrounded by nitrogen and oxygen. Then we can move to step 3. Step 3 is all about distributing the total number of electrons that we determined from step 1 by following 3 things. The first thing is to connect the atoms. So step 3A is connect the atoms. We have nitrogen connected to carbon and carbon connected to oxygen like so. And here, by forming these 2 bonds, we've used a total of 4 valence electrons. Then step 3B here, we want to complete the octet on the outer atoms. So that means that for nitrogen and oxygen, we want to add valence electrons to make sure that they have a complete octet. So we're going to draw 6 total electrons on nitrogen plus the 2 from the bond to carbon for a total of 8 electrons here. So nitrogen's octet is satisfied. And we're going to do the same for oxygen. We're going to draw 6 valence electrons plus the 2 from the bond to carbon. It has a total of 8 valence electrons. It has a complete octet. Then we can move into step 3C. Here, we're going to put any leftover electrons on the central atom. But the thing is, we actually have no leftover electrons. And that allows us to move into our last and final step. If the central atom has less than an octet, give it an octet by forming double and triple bonds from electrons on outer atoms. And this is where things get interesting, because for this molecule, there are 3 ways that we can form double or triple bonds to make sure that the central atom also has a complete octet. Now, the first way, all right, we're going to draw our first way that we can do this is we can take 2 lone pairs from the oxygen atom, and we can use that to form a triple bond between the carbon and oxygen atoms. So Let's go ahead and demonstrate that. So we have nitrogen still single bonded to carbon, but if we take two lone pairs from oxygen, we can form a triple bond between carbon and oxygen. Oxygen will now just have one lone pair. Nitrogen has all of it because we haven't taken any of those to form any double or triple bonds. So this is one potential structure that we can form. All right, that satisfies the octet for the carbon as well. Now, when you do this, because you know that there are multiple resonance structures, I highly recommend that you figure out the formal charges for each atom as well as you go. It's going to make things easier. And to do formal charges, we just follow our usual equation for that. So this would be a really good time for you to pause the video and try to do this on your own. See if you can determine the formal charge on oxygen, carbon, and nitrogen in this structure that we have just drawn. All right, so pause, try it out. And now I'm going to give you the answer. So in this structure, the oxygen has a +1 charge, the carbon has a 0 charge, 0 formal charge, and the nitrogen has a -2 formal charge. So that's one way that we can distribute electrons to make sure that the carbon has a full octet. But there's another way. We can take one lone pair from both oxygen and nitrogen to form double bonds, one between nitrogen and carbon, and the other between oxygen and carbon. And so we can have something that looks like this. Let me draw it out with purple, keep it consistent. We have a double bond right here and a double bond right here. And both the oxygen and nitrogen now have 2 electron pairs. All right. So now with this structure, we can also again determine the formal charge. All right. Pause, try it out on your own. In this structure, oxygen has a 0 formal charge, carbon also has a 0 formal charge, and nitrogen has a formal charge of -1. Now, the last thing that we can do to give us another resonance structure is take 2 lone pairs from nitrogen and form a triple bond between nitrogen and carbon. And that way, nitrogen now only has 1 electron pair left. And the formal charges on the atoms in this structure, for carbon it's going to be -1, for oxygen it's going to be -1, for carbon it's going to be 0, and for nitrogen it will also be 0. Now, these are the 3 resonance structures for NCO-. And now that we have assigned formal charges to each atom of each resonance, we can also work through our hierarchy to determine which one is the most significant resonance structure. So let's go over our rules, right? Let's try to figure out, is structure 1, 2, or 3 more significant, or are they all equally significant resonance structures? Let's work through our hierarchy. So our hierarchy is, first thing that you want to check, which ones satisfy the octet rule for all of the atoms? So if we're looking at this first structure, all 3 atoms have a complete octet. So in this first structure, nitrogen, carbon, and oxygen, all the atoms satisfy the octet rule. If we check structure 2, again, all 3 atoms in this structure satisfy the octet rule. They all have 8 valence electrons, so that's good. Structure 1 and 2, all of the atoms have the octet rule satisfied. For the third resonance structure, same goes. Each atom has a full octet. So then we can't use the first rule to determine which resonance structure is more important, because all 3 of these resonance structures have all their atoms that satisfy the octet rule. That means then we have to move into the second rule, minimizing formal charges. Structures with small or no formal charges are preferred over those with large formal charges. So if you look at structure 1, we have a formal charge on oxygen of +1, and then we have a formal charge on nitrogen of -2. If we look at the other 2 resonance structures, there's only 1 formal charge on just 1 atom. So that means we can go ahead and eliminate this structure as not being the most significant resonance structure. All right, so this first resonance structure is not the most significant. All right, so then we're stuck with 2 and 3. Which one of these is the most significant resonance structure? So that means we have to now move into the third rule. You want to, if you have formal charges, place the negative charge on the more electronegative atom. In structure 2, our -1 formal charge is on nitrogen, and in structure 3, our -1 charge is on oxygen. Which one is more electronegative? Oxygen is more electronegative. So you want that -1 charge on oxygen. And that helps us decide that structure 3, this one right here, is the most significant resonance structure. Again, our real molecule does look like a hybrid, a mix of all 3 of these, but the one that plays the most significant role in that is going to be resonance structure 3. So now you see how we can draw the resonance structures for a molecule and then work through our rules and hierarchy to figure out which structure is more significant. Now, with that, we can go ahead and move into our next discussion. Further on the point about Lewis structures and its shortcomings, the next topic that we want to cover is geometry and polarity. Because Lewis dot structures do not suggest or reflect the actual geometric arrangement of atoms in a compound, we need another system to provide this information, and one such system is known as the valence shell electron pair repulsions, or VSEPR theory. VSEPR theory uses Lewis dot structures to predict the molecular geometry of covalently bonded molecules, and it states that the three-dimensional arrangement of atoms surrounding a central atom is determined by the repulsions between bonding and non-bonding electron pairs in the valence shell of the central atom. These electron pairs, they arrange themselves as far apart as possible, thereby minimizing repulsive forces. And the following steps are used to predict the geometrical structure of a molecule using VSEPR theory. So the first thing that you would want to do is draw the Lewis dot structure of the molecule of interest. Afterwards, you want to count the total number of bonding and non-bonding electron pairs in the valence shell of the central atom. Then you're going to arrange the pairs around the central atom so that they are as far apart as possible. And to do that, you want to follow a chart to help you figure out that geometry based off of regions of electron density. This table lists the 5 most common electronic configurations of molecules. And so what we're looking here is at a list of electronic geometries. Electronic geometry describes the spatial arrangement of all electron pairs around a central atom, including both bonding pairs, which form bonds with other atoms, and lone pairs, which are not involved in bonding. So we're going to go over this table first. So if you have 2 regions of electron density, this is what the geometric arrangement would look like. The shape is linear, and the angle between these bonds is going to be 180 degrees. Now, if you have 3 regions of electron density, the geometric arrangement looks like this. There is a 120-degree bond angle here between each of these bonds, and this shape is referred to as trigonal planar. With 4 regions of electron density, our geometric arrangement looks like so, and this is called tetrahedral, and the bond angles here are going to be about 109.5 degrees. With 5 regions of electron density, our shape is trigonal bipyramidal, and it looks something like this. Now, depending on which angles you're looking at, our bond angles can be 90, 120, or 180. With 6 regions of electron density, we have octahedral geometric arrangement, and it looks something like this with your central atom here and 6 different bonds. And the bond angles here, depending on what you're looking at, can be 90 degrees or 180 degrees. Now, again, this is a table that summarizes electronic geometry. And the concept of electronic geometry is going to be compared to molecular geometry here in this next table. So I just want to clarify again. The concept of electronic geometry, and now what we're going to cover, molecular geometry, is really fundamental to understanding the shape and behavior of molecules. Again, electronic geometry, which is what we saw in this table, describes the spatial arrangement of all electron pairs around that central atom. So this is going to include your bonding pairs and your lone pairs. This geometry is determined by the regions of electron density around the central atom. So for example, if we look at a molecule like CH4, methane, you're going to have carbon bonded to 4 hydrogens. And that means that the central atom has 4 regions of electron density. If we look at something like ammonia, NH3, this is going to have a nitrogen bonded to 3 hydrogens, and it's also going to have a lone pair. So it will also have 4 regions of electron density. Similarly, if we look at water, H2O, you're going to have an oxygen bonded to 2 hydrogens, and then it's going to have 2 pairs, all right, 2 lone pairs. And so it also has a total of 1, 2, 3, 4, 4 regions of electron density. The electronic geometry for each of these molecules is going to be tetrahedral, all right? All of these molecules have a tetrahedral electronic geometry. Now, here is what we're going to contrast it to, molecular geometry. Molecular geometry, on the other hand, focuses only on the spatial arrangement of the bonding pairs of electrons, ignoring the lone pairs. And so, while methane, ammonia, and water all have the same electronic geometry, their molecular geometries differ due to the presence of lone pairs. So for methane, CH4, it had 4 bonds, no lone pairs. And so we would go here on our table to 4 regions of electron density, 0 lone pairs. This would land us right here. It would also have, methane, a tetrahedral molecular geometry. What about ammonia, NH3? It had 3 bonds and 1 lone pair. It would actually have then a trigonal pyramidal molecular geometry. What about water? It had 2 bonds and 2 lone pairs. It would have an angular or bent molecular geometry. And so you notice that all these molecules, all 3 of them, had the same electronic geometry, but different molecular geometry. And so this table does a really good job of helping you work through what the molecular geometry would be, all right, for each region, all right, for each number of electron-dense regions versus number of lone pairs. So if you have 2 regions of electron density, 0 lone pairs, you have linear. If you have 3 regions of electron density, 0 lone pairs, you have trigonal planar. But if you have 1 lone pair, then you have angular or bent. And we just worked through for 4 regions of electron density, no lone pairs is tetrahedral. 1 lone pair, your molecular geometry would be trigonal pyramidal. 2 lone pairs, angular or bent molecular geometry. And so on and so forth. Here for 5 regions of electron density, 0 lone pairs, we have trigonal bipyramidal. 1 lone pair, we have seesaw. 2 lone pairs, we have a T-shaped molecular geometry. And for 3 lone pairs, we have linear. For 6 regions of electron density, 0 lone pairs, we have the molecular geometry octahedral. But with 1 lone pair, our molecular geometry is now square pyramidal. 2 lone pairs, it's square planar. 3 lone pairs, it's T-shaped. And 4 lone pairs, it is linear. So again, it's really important to be able to distinguish between electronic geometry and molecular geometry. This is going to be extremely important. Now, with that being said, we can move into a discussion now on the polarity of a molecule. The polarity of a molecule is determined by both its bond dipoles and its molecular geometry. That's why we held off on talking about the polarity of a molecule as a whole. It's because we first needed to understand the concept of molecular geometry. It was easy to determine the bond dipole for something like hydrochloric acid, where you only have 2 atoms. But what about for more complicated molecules? Now, a bond dipole, this occurs when there's a difference in electronegativity between the two atoms in a bond, and this results in an unequal sharing of electrons. So for example, if we look at water, the OH bond that you see here in water is polar because oxygen is more electronegative than hydrogen. And so for this one bond, we can draw a bond dipole. The arrow points towards the more electronegative atom, so towards oxygen, all right? And that results in a partial negative charge on the oxygen, partial positive charge on the hydrogen. However, it's important to note that the presence of polar bonds does not always mean that the molecule as a whole is polar. The overall polarity of the molecule depends on the vector sum of the individual bond dipoles, and that's really influenced by molecular geometry. So if we look at water, for example, for the first OH bond here, we drew a bond dipole like this, and we could do the same thing for the other OH bond right here. There's a bond dipole like this. Now, what is the overall dipole moment for the whole molecule? Well, something to remember, and this is discussed in my physics playlist if you need a reminder on vectors, is we can break these vectors down into the X component and into a Y component. And if we do that for both of these vectors that we've drawn here for the dipole moments of each bond, we would notice that the X component of both dipoles will cancel each other out, but the Y components are going to build on top of each other. And so that means the dipole moment for the whole molecule is going to be drawn like this, straight up. All right. Now, something else to note is that if the molecular geometry is such that the bond dipoles cancel each other out, the molecule is then nonpolar. So a molecule can be nonpolar because it has nonpolar bonds, but a molecule as a whole can also be nonpolar if all its bond dipoles cancel each other out. A good example is carbon tetrachloride. So CCl4. This is carbon bonded to 4 chlorine atoms. Each of these bonds to chlorine, these chlorine carbon bonds, all of them are polar bonds. And we would draw the arrows up towards the chlorine atom because it's more polar, it's more electronegative than carbon is. So there are 4 polar bonds in this molecule, but because the molecule is tetrahedral and the bond dipoles point towards the vertices of the tetrahedron, and they cancel each other out actually, and that results in a total nonpolar molecule. So it's important to be able to think about things in this way so that you are able to determine for molecules as a whole if they're polar or non-polar. With that, we're going to move into our last topic in Objective 3, which is about atomic and molecular orbitals. Let's touch up on atomic orbitals again. Atomic orbitals are regions around an atom where electrons are likely to be found. These regions, they have specific shapes and are crucial because they determine the distribution of electrons in atoms, influencing the electronic and reactive properties of atoms. Now, according to valence bond theory, covalent bonding occurs when atomic orbitals overlap. Now, when electrons are considered as waves, what does this mean for us? That means that their interactions can result in either constructive or destructive interference. Constructive interference is when electrons are in phase and they interact, and that interaction produces a wave with a larger amplitude leading to a bonding orbital. Now, destructive interference, this is when electron waves are out of phase, and when they interact, they produce a node. This is a region where the probability of finding an electron is 0, and this leads to an anti-bonding orbital. And so, in short, valence bond theory states that bonds result from constructive interference of electron waves. Now, when two atoms bond to form a compound, their atomic orbitals interact to form molecular orbitals. A molecular orbital describes the probability of finding bonding electrons in a given space, and this formation is qualitatively described by the overlap of two atomic orbitals. Now, in previous chapters, we discussed the 4 quantum numbers that describe the energy and position of an electron in an atom. The principal quantum number n indicates the average energy level of orbitals, while the angular momentum quantum number L describes the subshells within each principal energy level. When L equals 0, this indicates the s subshell with a spherical orbital. And when L equals 1, this indicates the p subshell with 3 orbitals shaped like barbells along the x, y, and z axis. Now, these orbitals and these lobes, they have signs. The signs of the lobes of these orbitals, positive or minus, all right, positive or negative, they're assigned mathematically, and it's actually a complicated topic that we can get into, but it's not necessary for a general chemistry course. So we'll keep it very baseline here. But these assignments of positive and negative lobes, they play a role in bonding. If the signs of the 2 atomic orbitals are the same when they interact, a bonding orbital forms. And if the signs are different, then an anti-bonding orbital forms. And there are 2 main patterns of overlap that we want to talk about in this course that are observed in the formation of molecular bonds. When orbitals overlap head to head, a sigma bond is formed. A sigma bond, all right, allows for free rotation about their axis because the electron density of the bonding orbital is a single linear accumulation between the atomic nuclei. Single bonds are sigma bonds resulting from the overlap of 2 s orbitals, not 2s like this, but 2 s orbitals, all right, being overlapped. All right, so single bonds are sigma bonds resulting from the overlap of s orbitals. Now, when orbitals overlap in such a way that there are 2 parallel electron cloud densities, a pi bond is formed. Pi bonds do not allow for free rotation because the electron densities of the orbitals are parallel and they can't be twisted to allow continuous overlapping. Double bonds, they consist of 1 sigma bond and 1 pi bond. So you can see that pi bond right here because we have these 2 p orbitals coming together to overlap. We have these 2 regions of the same sign, quote unquote, keeping it simple here, that form these 2 regions, all right, these 2 parallel electron cloud densities. And so this is an example of that. And a double bond, all right, consists of 1 sigma bond and this 1 pi bond, which we see right here. Triple bonds, they consist of 1 sigma bond and then 2 pi bonds. Now, this topic can get really complicated really fast, and if you're interested, then I highly recommend you take an inorganic class during your semester or whenever, because it will go into a lot of depth into this topic, and it'll also give you a mathematical background for some of this information that you might be like, well, why is it this way and not that way? But we want to keep it general here in our general chemistry class. If you're interested, though, let me know, and maybe I can create a quick extra lesson just for funsies on this topic. But with that, we can actually move into our final discussion on intermolecular forces. Intermolecular forces, these are weak electrostatic interactions between atoms and compounds, significantly influencing physical properties like melting and boiling points. Now, there are 3 main types of intermolecular forces that we want to talk about: London dispersion forces, dipole-dipole interactions, and hydrogen bonds. Let's go ahead and get started first with hydrogen bonds. Hydrogen bonds are a specific, unusually strong type of dipole-dipole interactions. A hydrogen bond occurs when hydrogen is covalently bonded to one of 3 highly electronegative atoms: nitrogen, oxygen, or fluorine. In this bond, the hydrogen atom carries only a small amount of the electron density, essentially acting as a naked proton. The positively charged hydrogen atom will then interact with the partial negative charge on a nearby fluorine, oxygen, or nitrogen atom in adjacent molecules. And this interaction is significantly stronger than regular dipole-dipole interactions, though still only about 10% as strong as a covalent bond. Now, substances exhibiting hydrogen bonding often have unusually high boiling points compared to similar molecular weight compounds that do not form hydrogen bonds. And this is because breaking hydrogen bonds requires more energy. So you can see an example of hydrogen bonding right here. You have this oxygen hydrogen covalent bond. And because oxygen is more electronegative and it pulls electrons more towards it, it has a partial negative charge, and hydrogen has a partial positive charge. And here we see another water molecule. The oxygen atom of one molecule can interact with the hydrogen atom of another water molecule, and this forms this electrostatic interaction that we refer to as a hydrogen bond. Now, the next thing we want to talk about is dipole-dipole interactions. We just said that hydrogen bonding and hydrogen bonds is an unusually strong type of dipole-dipole interactions. So it's important for us to understand what a dipole-dipole interaction is. These forces occur between polar molecules where there is a permanent dipole moment. Dipole-dipole interactions, they arise from the attraction between the positive end of one polar molecule and the negative end of another. It is important to note that dipole-dipole interactions only occur in molecules with permanent dipoles. Nonpolar molecules, they do not exhibit these interactions, but they can still experience London dispersion forces, which we're about to talk about. But you can see here, right, we have HCl and the hydrogen atom in one hydrochloric acid can interact with the chlorine atom of another, and that's because there is a dipole that happens in this HCl bond right here, because chlorine is way more electronegative, all right? It has a partial negative charge, hydrogen has a partial positive charge, and therefore these interactions can happen. Notice that this is not a hydrogen bond because this hydrogen is interacting with a chlorine. And we specifically defined hydrogen bonding to be a hydrogen interacting with either a nitrogen, oxygen, or fluorine specifically. So this right here is a dipole-dipole interaction. Forces occur between polar molecules where there is a permanent dipole moment. Now, the last intermolecular force that we want to talk about is London dispersion forces. These are also known as dispersion forces or London forces. They are the weakest intermolecular forces, and they occur between nonpolar molecules. They arise from temporary fluctuations in electron distribution within molecules. So as electrons are always in motion, they can create temporary and uneven distributions of electron density, leading to the formation of temporary dipoles. These temporary dipoles induce similar dipoles in neighboring molecules, resulting in a weak attractive force between them. And despite their weakness, though, London dispersion forces, they play a crucial role in the properties and behaviors of a lot of substances. With that, we have covered everything that we want in this chapter. This chapter was long and there was a lot of important topics to cover. In the next video, we're going to tackle some practice problems together to make sure that we truly understand all the concepts that we discussed here in this bonding and chemical interaction lecture. With that, let me know if you have any questions, comments, concerns down below. Good luck, happy studying, and have a beautiful, beautiful day.